Okay, we're on the Thursday lecture at the first end after spring break. Interesting comedy that I took as a comedy, although I'm sure it wasn't intended that way, when the chancellor wrote all of the faculty and staff an email welcoming us back after spring break on Tuesday. And I thought, they've never done that before. Why are they doing that now? And it's just like, all he can say over and over again is thank you, thank you, thank you, thank you. And, well, he wrote another one today, but I haven't looked at it, and I'm sure it has at least a half dozen thank yous in it. But we're all in this together, so moving along. I did fix a hints page that I had reposted yesterday after I had a video session with Colton and Will, and that's what prompted the extra hints on the homework. Actually, I think I'm going to start with the homework because I'm going to clear the deck on that because that's due tomorrow. A number of people have turned that in already, but even some of you that have turned it in, I want to make sure you understand what you were doing when you did problem number 6, because you may have lost track of it in the whole business there. So first I'm going to bring up this app that I showed you a couple of weeks ago when we were talking about sampling theory. Remember, when we have low-pass sampling theory, we simply have to sample at greater than twice the highest frequency to make sure we don't have any aliasing. And once we do that, the blue spectrum here is in the clear. When we have a bandpass signal, we have something considerably different, though. If we sample at greater than twice the highest frequency, we're good to go, but we're using a very high sampling rate, much higher than what we might really need. And the other thing is, when we're sampling a bandpass signal, we eventually want to downconvert it, like in a coherent demodulator for double sideband. We want to downconvert it down to baseband or close to baseband. So problem number 6 is investigating some of the issues behind that and how a software-defined radio purposefully undersamples because the bandwidth of the signal, which is shown, I'm pointing my arrow at right now, is much less than the highest frequency that we're trying to capture. So to demonstrate it again, when I undersample, I start to introduce aliasing, but the aliasing is controlled aliasing. And say if I stop right here, the blue spectrum is still intact, and because the blue spectrum is probably a radio signal, we actually might be able to work with the red spectrum, in fact. So if we continue to drop the sampling rate more and more, we're moving the translates around. And in the homework problem, I'm constraining that you design the undersampling rate fs to place a spectral image right at 1/4 the sampling rate, which on this plot would be at 0.25. A question came at me yesterday, what's the significance of 0.25? Well, 0.25 is such that once you can convert it by undersampling down to 0.25 and also a copy over here at minus 0.25, you can then do a complex frequency translation to bring it all the way to baseband. Complex frequency translation will take the entire spectrum we see here and shift it left or right. If we just simply multiplied, as in coherent demodulation, to try to bring it down to baseband, we would take the negative spectral image and bring it up to 0, and the positive spectral image here and bring it down, and they would be on top of each other and they would be flipped relative to one another, and in general that's going to be a failed operation. So it's a two-step process, but you're just looking at the first step. So in this example, again, remember you can come down tighter and tighter by undersampling, and that's no good right there, but there. That is the absolute tightest you can go, but there's no guard band in there. So what I ask you to do in the homework problem is actually make the sampling rate just a little bit higher so that there's separation between these spectral translates, which could be recovered with a filtering operation in using digital signal processing. So, and the other thing to note is that m, that integer that you solve for, m, is the undersampling factor. So it kind of indicates how many translates are going to be on the interval 0 to fs, which in this case is 1.0. So things are related to this picture, and I'm hoping that this picture helps you, motivates you to understand what you're trying to do. This application is available on my website. It was written for the Signals and Systems for Dummies book, and it was written in a programming language called Zojo, which you can download a free copy of. You just can't distribute the executables without buying a license, but you can develop as much as you want on your own machine in the debugger. And I guess that's all I have to say about that. But hopefully this re-energizes you into thinking what this is all about. It's about sampling and converting in frequency all in one step. And it's a fairly common technique in software-defined radio. It's very likely being used inside your cell phone and some other wireless devices that you have. Okay, so now we're going to move on to talking about, let's see, this application called PDF, or Drawboard PDF, has crashed 3 times on me in the last 15 minutes. Hopefully it will at least come up with what I've got for today. So I gave you the introduction to the undersampling and so on, and I decided what I would like to do here is just go back and make sure you're solid on both the homework problems. The first homework problem you're turning in is modified slightly from the drill problem, but the idea is you want to pack each of those channels into a serial bit stream in order to transmit them using time division multiplexing. So you, in this example here, I just have 2 channels, and I have a bandwidth W1 for one channel and a bandwidth W2 for the other channel, and the bits needed per sample are B1 and B2. And then from the sampling theorem, that's where the 2 comes from. We have to sample at twice the highest frequency, so 2 times W1 and 2 times W2, and then we take B1 bits per sample. So that gives us our serial bit rate in kilobits or megabits per second. And then the second part of the problem is, if you're going to transmit those bits, and those bits have bit period TB, if you're going to put them up on a carrier, and I'm just going to show this as a single-sided spectrum, but I'm going to suppose that's the carrier and somewhere's down over here is 0. So the pulses, rectangular pulses, are of width TB. You know, from, I think it was problem number 5 on the exam, the spectrum is going to be something like that. And we know that the nulls in that spectrum are going to be at FC plus 1 over TB and FC minus 1 over TB. And the total bandwidth occupied by that is roughly 2 over TB, or twice the serial bit rate. So I kind of just gave you the answer to that, but that's what I'm looking for there. If you have to transmit that signal on a carrier, this is using rectangular pulse shapes, which have a sinc function for their spectrum. That's what we're talking about to support that transmission, the bandwidth that's required. Anybody have any questions that's got their microphones on and want to talk back to me or message back to me? Yes, you sound crystal clear. I've got my headset on, so you sound really clear. Yeah, it is. It is. Okay, moving down to the second problem. I put up this long paragraph to kind of motivate you to go do something, but Then when I got questioned yesterday a couple of times, I said, okay, I'll write this out some more. So what I actually hint at in here is I say, what the best starting point is, I said find, work from the equality equation and find two hard equations that are not inequalities that relate FIF to M and FS. So this is the equation. That's the only equation I have in that problem. And when you unwrap an absolute value sign, you have to unwrap it in order to drop the absolute value signs, you have to write it as two equalities then, one with the minus sign, one with the plus sign. When I first wrote this out, for whatever reason, a stray mark was there indicating it was a minus sign. I never intended to do that, but at any rate, one's plus and the other's minus. And when you put that together, you get this equation right here, which has a plus and minus in it. So it says we need to, our FIF value is going to be at M plus and minus 1/4, that quantity times FS. And that's how you go about working this problem. You pick a value for FS, and the equation up here tells you that you've got to make, this equation, when you spin it around, you've got to have FS greater than or equal to 2 times B. Strictly greater than is better because it gives you a guard band that you can do some filtering work with. But at any rate, that should make sense to you because from the low-pass sampling theorem, it says we have to sample at greater than twice the highest frequency. And now for the bandpass sampling theorem, it's saying that if it can work at all, we're going to have to sample at least twice the bandwidth of the bandpass signal. So hopefully that sits well in your mind, because I worked for somebody at a local company. I won't mention the name since I'm not going to say something that's super kind. It's just a fact, though. And that manager said, well, you can. All you have to do is sample at 2 times the bandwidth of the signal. And I said, well, you have to be careful, because if we went back over to here, and we were looking at this spectrum over here, it's possible that you'd have a collision if you did that. You might have something bad happening down in here where you'd have some spectra overlapping. So it's really just, you can go no lower than that on a good day, but it might not come out perfect. So at any rate, moving along, you can pick an initial guess value. Yesterday when I was working with Colton and Will, I said let's look at setting Fs equal to 2 times B, so that was 400 kilohertz or 0.4 megahertz. And that got one solution. And then when I did this last night, I just put in 0.45. And then I set a value of M to range over, and I had this Python code that just prints out values of FIF, either the plus solution or the minus solution. And when it lists those values out, I get to look at them and say, which one would I like to get? I can see that I cannot put my IF exactly at 10.7 and keep an integer value for M, but I can get a value that's pretty close. So you can see that for 0.45 FS, I can get FF or FIF to be at 10.6875, and that's pretty close to 10.7. So that's using the 24th subharmonic or 24th subband in the undersampling operation. So I take a look at that, and I use the function that I put in the Chapter 3 notebook, plug those values in. I say the IF frequency is going to be 10.68, so I set right in here. I'm saying that my bandpass signal, if I go way up here and plot what it looks like, it's going to be sitting somewhere up in here. and the center of it's going to be at 10.6875, and then I'm saying the bandwidth of that signal runs from 0.1 megahertz below and 0.1 megahertz above, so that defines the bandpass spectrum. And then for plotting purposes, I'm just setting 25 translates to plot, and that's how many images I make it create. Again, if I go back over to here, I can't have my software plotting an infinite number of these images like we know exists in theory, because that would take too long. It would never happen. So I just set a goodly number of translates, at least enough to make sure that I have overlap so I can see all the aliased components that I'm wanting to see without getting confused. So I do that. I set the sampling rate to 0.45, and then I have F sweep from -12 to +12. This would be in megahertz. But after I get my plot, I do some scaling on the plot and X limiting the plot to just zoom in on the translates that are sitting around 0. And sure enough, I see exactly what I was hoping to see. I see right at Fs over 4, which is 0.225 megahertz, I've got one translate, and then on the other side of that, because it's a real signal, I have a symmetrical spectrum. And because I set the sampling rate above 0.4 megahertz, I have a little bit of a guard band in here in between all of the translates. So this is good. If you wanted to try another value, which I'm asking you to do, which you have to do from the homework, just pick a different value. Pick 0.5, let's say. You'll have a bigger guard band, and the larger you make the sampling rate, the lower the undersampling factor will be. You won't be able to get by with 24. You'll have to drop M down lower to have the translate spaced out further. So you might have to change this range from 15 to 20 or something like that. Who knows? You just got to look at the numbers you're getting when you solve this equation. And I don't know if this seems like bad engineering to you, but it's a situation where we can't just write a closed form expression and know the answer. We have to iterate to find the answer. So that's what we're doing. And I find this to be an acceptable way of doing it because it gives me a better sense of reality to actually just plug a guess in for M, because I don't know beforehand which one's going to work. And in this case, I'm trying to get an M that gives me an IF frequency that's close to where I want to operate. And that kind of leads me in as a segue to what I want to do next, and that is look at some mock quizzes, and then we'll do the project. So, any questions? Okay, I feel like maybe this is the dead horse that I've beat beyond reality, but I want to make sure you understand it, because some of these things are pretty much bread and butter things that I'd like you to be able to take with you and use on the job. Just saying, oh, I know about sampling theory and I know software-defined radio. I can play neat games like this. Okay, so the next thing I want to do is kind of back up a little bit. Since we've been talking about translation, frequency translation, and sampling, I decided rather than jump on the project, I would go through these mock quizzes. So these are quizzes that have been given before, but I didn't squeeze this one in before the break. And then the second quiz would have been, like for this week, let's say, it would have been over the homework problems for this week. But I decided not to give a quiz, so I've had this up for probably over an hour now, so has anybody worked it? Okay, are you using an analog discovery? Don't bully you? I just was wondering if you bought them because I had asked. Okay, that means you can use it for the CommLab too. But now, Did you buy the $20 software-defined radio dongle? Okay, that is more fun for that Lab 6, but that's another topic. That's a very fun gadget to play with if you are into software-defined radio, which a comm theory student ought to be. So what's this quiz? This first part of the quiz is all about, and actually the whole quiz is about this. This is on frequency translation and mixing. I created this quiz a few years ago. I like it a lot because it's pretty practical. It deals with Wi-Fi, and some of you have looked into the details of setting up your wireless router or know the channel number you're on. You maybe didn't know the exact frequency that you're on, but remember when we looked at the beginning of the semester at the frequency spectrum allocation chart for the entire United States, and we looked in the neighborhood of 2.4 gigahertz and saw a lot of services crammed into that area. So this is the ISM band, instrumentation, or industrial, scientific, and medical. Excuse me, that's what ISM stands for. So it's unlicensed band, and this is where microwave ovens also sit with their magnetron high-power microwave devices for cooking our food. So these are the original Wi-Fi channel allocations. They're each 22 megahertz wide. They overlap each other. So I took this right off of the Wikipedia, I believe, for Wi-Fi. And you can see how if you're going to coexist, and this is actually part of what the unwritten lab for the comm lab was going to have you do. You were going to go with the antenna and the field fox and go sit near different buildings on the campus and just see if they're abiding by this spectrum allocation. In other words, in a given building, like say the engineering building, if they're wanting to allocate a full 22 megahertz for the higher data rates supported by Wi-Fi, they should be, get my pen working here, they should be only at, say, 1, 6, and 11. If they tried to use a frequency closer, then they'd be causing interference with each other. I'm not sure exactly how the IT department for the campus sets things up, but the curiosity on my part was to go investigate and see if they've got things allocated somewhat in that fashion. And then where's the Wi-Fi that's along the pathway on the campus where they've got the wireless access nodes outdoors? I don't know. Just curious, though, and those of you that live in apartments know that you're all crammed in there on what you can pick for your channel. But this gives you an idea of how the Wi-Fi channels are allocated. And of course, a given Wi-Fi channel doesn't have to use its full 22 megahertz, and because it switches between modes, it down selects to go to a bit rate that is supportable by the local interference and environment. But this problem was all about frequency translation, super heterodyne principal ideas, things that those of you in the lab did in Lab 4, and in general it was something that we had homework problem on already that you've already turned in. So I gave you the spectrum, and I said find two choices for the local oscillator frequency that will translate channel 6. So I was picking this one right here, which is centered at 2.437 gigahertz. Translate it to 160 megahertz. So I had read an article, I think it's an IEEE article, that somebody had written on an integrated circuit, RFIC, for Wi-Fi, and I took that block diagram and pasted it in here. So it's just showing you what we need to do to build this. So in the block diagram for the RFIC, they show an image rejection filter outside the chip. They show an LNA that's in the chip. They show an RF mixer that's in the chip. Then they show an IF filter that's outside the chip, and then IF amplifier, and then some additional down conversion and mixing. to go into the digital domain. So this whole back end is really just to get it converted to discrete time. In other words, use DSP for everything else after that. So in this problem, though, you're just finding initially the local oscillator frequency. So what would be the choices for that? So some people have their microphones on. If you don't have your microphones on, though, you can Slack channel message me. I'm calling it FLO1 and FLO2, but I really just mean are the two choices. What are the two choices we can have here to take something at 2.437 and in my household they've been watching Jeopardy here in the evening, so if you want to sing that jingle you can while you're thinking of your answer. But it'd be the question, but I'm asking you for the answer. Okay, so 2.437 plus 160. So that's one answer, and let's see, let's see. And John put his answer up in his own private channel, so I don't see what else he wrote in there looking at one computer. But 2.437 plus and minus. Okay, well then you'd get a negative frequency, so I'd rather write it as 2.437 plus and minus 160, right? I think what you said, Colton would... No, because it's 0.16, it's gigahertz, right? We want to have the units the same, so those are the two options right there. So I'll just take this one and multiply and add this one up, so 2.597. In this one I have to subtract, so I have to think harder because I have to borrow to do that. I don't have my tool running, but I'll just go with a positive one for now. I don't want to get too carried away with the math. So 2.597 gigahertz. This would be the high side tuning local oscillator, and then it will down convert it. So what is the image frequency going to be? Let's just, in this case, take the image frequency associated with the high side tuning. So remember I told you before that a good thing to do is to draw a little picture. So you want to convert to 0.16, and you're up here at, I'll just kind of compress the scale axis here and pretend that there's a cut there. So this is pen's failing on me a bit. 2.437 and, oh, wait a minute, I didn't want to do that. I did get myself confused here. Let me erase that. So that's our carrier frequency, and we decided to put our local oscillator frequency at 2.597. So our signal of interest is right there, and that will convert it down to 0.16. And then if we go another IF frequency above the local oscillator, that will be our image frequency. So that's going to be another 160.16 onto 2.597. So that's going to be, let's see, 6, 7, 2 point, I'm just trying to add another point. I'm going to be adding 0.32. So 0.32 is 0.7, yeah, 2.757. Thank you, John. Oops, took me over to the slot page. So that would be our image frequency right there. And then we'd have the image frequency for the low side if we wanted to. Does everybody get that? So that would be at 2.757 gigahertz. Could also get in and down convert to 160 megahertz. Then the IF, then the image is going to be below, so I can do that. If you're wondering why I'm doing this stuff today, it's because, hey, we're going to have an exam over this eventually, so I need to just keep pushing away on stuff. So if we did that, we'd be sitting over here at 2.437. Then our local oscillator would sit below that, and I just didn't do the math on that. Somebody want to punch those numbers in? It's going to be 3, and then it's going to be 2. Okay. So that's this guy right here. And then we're going to go another 160 below that for our image. So 2.117. So if I was to keep the same colors as I had, our signal of interest is right here. Signal not of interest. Our image is sitting right there at 2.117. And that will down convert here to 0.16. So we have two images. So set that aside for a second. Then move on to the third related topic, and that is what is the bandwidth that we need for this SAW filter, and that's this element or component up here. It's centered at 160 megahertz, but we need it to just pass our signal, and yes, give or take anything, probably a little bit of pad in there, but 22 megahertz is the answer that I was looking for. John, who's kind of the expert on this stuff from his line of work, what would you pick? Okay, well, we're going to see an example of a commercial part on the next page. Okay, before going on though, because I do have the solution on the next page for the last part here, what is the purpose and what are the requirements of the image reject filter? So, what's the purpose of the image reject filter? We just talked about the image, right? We know that they're, depending upon how we choose the LO, one's at 2.757, the other one could be at 2.117. So what does this image reject filter have to do? Yeah. Yeah. And the 2.757, where does that exist? So if you look at this, you can say 2.757, that's above the Wi-Fi bands. And the other frequency, 2.117, is below the Wi-Fi bands. But and this is a little bit hard for me to show without animation. If I was looking at tuning to a higher Wi-Fi band, then the image frequency is going to come up, and this image, pardon me? Sure. I've got more details on the next page, but I just want to stay away from that for a moment. Yeah. It's outside, you mean? Yeah. When you say leaving your band, you're saying leaving it wide open? We're not leaving our allocated space. We're trying to protect ourselves from something outside the allocated space from ingressing into our system, though. That's the way I'd look at it. And it's another thing that's important to note is that we don't have both image frequencies to deal with simultaneously. One is associated with, this one's associated with low side, and this one is associated with high side. So they don't both exist at the same time. When you make your decision, though, which you're going to use, then you have one or the other of those two that you have to contend with. We're not emitting frequencies intentionally. These are frequencies that our receiver could receive and would land on top of. Like in this picture over here, I was trying to say if we're in the low side tuning, that signal will land right on top of the green signal that we want to get. The image will, yeah, we're unfortunately going to have that happen. Yeah, well, you have to filter it out right here. And the reason why the image rejection filter is put there is you don't want to put it ahead of the low noise amplifier because it will create a noise figure issue. We're going to discuss noise figure and noise in receiver front ends in Appendix A at the end of later this month, let me just say. So we will get into that. It's kind of a hybrid area between electromagnetics and comm systems. I happen to think it lands more firmly in comm systems because we're the systems people, but at any rate, we will be getting into that, why that filter is after the low noise amplifier. However, here's a good however question. The low noise amplifier is not protected, so if the signal at the image frequency is very powerful, it could overload the LNA and make it difficult to receive our desired signal just because the LNA didn't have enough headroom to support a strong out-of-band signal. Yeah. Exactly. Are you guys hearing that? I think it's safe to say that no system is bulletproof. I mean, there's always some vulnerabilities that allow it to be exploited somehow or another. So let's go on to the next page and just, so the requirements of the image rejection filter are that it has to be able to block that 2.117, but in general it has to actually block a wider band if we want to be able to select different Wi-Fi frequencies. And presumably here in the real Wi-Fi receiver, this is tunable so that you can set your receiver on whichever Wi-Fi channel you want to run your network at. So let's just go over here and look at how this would pan out. When I originally wrote this problem, I created a more detailed solution just to satisfy curiosity, because I think we use Wi-Fi so much, we're like, I want to understand how that works and why it doesn't always work. So here's a more detailed look at what the image rejection filter would have to do. And I haven't looked at this for a while. I'm thinking, yeah, this is for high side tuning. So this is, I think this picture was developed for high side. Why do I know that? Because I see the image above the desired signal, and that's the scenario that we had over here. We'd have a symmetrical version of this for the other side, but the image is 2 times the IF away, so the image reject filter has to have a bandwidth that cuts off right in here, bandpass filter, so that it doesn't let that image in, but then it needs to be able to handle signals over the entire bandwidth. So it's going to be some sort of a bandpass filter, and that's what I showed down below here. Actually, this is low side, high side. So if you design a bandpass filter, you can just have it cover the Wi-Fi channels, and it turns out, taking into account the 22 megahertz, which half of 22 is 11, so that's why the 11 shows up in here. A 94 megahertz filter can do that. So that's what you need to go off and buy. I didn't go shopping for those, but I did go shopping briefly for an example of the 160 megahertz IF filter, and that's the other filter that we talked about, because we said this would have to be 22 megahertz, centered at 160. So I just decided I wanted to go see what could I buy off the shelf for that guy, and I didn't have to look for very long, and I found that there was an importer from China Electronics Technology Group, that sells this part. It's a 160 megahertz SAW filter. It's spec'd at 22 megahertz minimum bandwidth. Sure. It depends on how it's designed. Believe it or not, when I was in school, I had a microwave class that talked about components, and we talked about surface acoustic wave devices. So a surface acoustic wave filter is made on a substrate. It's usually lithium niobate, or at least that's the way I learned it. And it has fingers as a transducer element. So if you hold up your right hand and spread your fingers apart, and then you hold up your left hand and spread your fingers apart, and thinking of them together, it's an interdigitated kind of a structure where you launch an acoustic wave over the surface of the crystal, lithium niobate, and then it propagates towards the other set of fingers, and it forms a response like what you said, I think, Colton. It could be a Hanning or Hamming or something like that. I don't really remember the intimate details, but it's an analog version of an FIR filter in a sense, based on these interdigitated structures. And maybe, John, you know more about this because you've probably bought these before or spec'd them before for a design. Yeah, so rectangular. Yeah. Yep. Yeah. That's a lot. But look how perfectly rectangular it is, though. And if, again, I don't design stuff in this area, but if the environment is hostile to some extent, and I know in my household the microwave oven wipes out my Wi-Fi, and I think it lies just to one edge of the Wi-Fi bandwidth, but it still gets in and degrades the network. I just picked this out of the catalog because I thought people are making these parts. If you were a vendor, you would say, oh, there's going to be a big market for these because there's lots of Wi-Fi devices out there, and you can't put that part on the chip. So it's an off-chip component, and that's made sense to me at the time. There's probably other filter technologies that could be used in this area, but SAW filters and another class of acoustic wave filters is BAW, bulk acoustic wave filters, that are out there used in cell phones and things. It's interesting though, right? Any one of you in this class, this could be your specialty. You probably wouldn't be doing it in Colorado Springs, but you could work for a company that does this. You'd be what? Okay, well, when we're allowed to travel again, yeah. The company I'm thinking of is RF Micro Devices, which I think was originally in South Carolina, but they have divisions in California because they bought another company that does the BAW filters, bulk acoustic wave stuff. They're somewhere over by you, John, aren't they? Yeah, RFMD. The company I'm thinking of is Quora or Q something or another. Yeah, Qorvo. That's what I'm thinking of, Qorvo. Maybe. I don't remember. I've got some of their filters in my office, though, because I bought them for a project with a student, and then we never utilized them. They were free samples, though, for a cell phone band for 4G cellular stuff. Okay, enough of that. I'm just trying to get you more excited about this stuff, and I think it's easy math. The design of the components is not easy, though. So, okay, the second quiz is on sampling, and I may not do much on FM today, but I wanted to backfill on this. So, this first question is just on sampling. So this is just using the sampling theorem. So if you use the low-pass sampling theorem, what do you have to look at? This sinusoid is at 15 kilohertz. And then what are the frequencies associated with the second term? Since it's a cosine squared, we're going to have what two frequencies come out of here? When we square a cosine, what do we get? We get 1/2 plus 1/2 twice the frequency, right? Okay. Yeah, so that would be a doubling and then a difference, which would be 0. So the difference is DC, and then the doubling is going to be 10 kilohertz. So from the low-pass sampling theorem, Fs must be greater than, and I like greater than rather than greater than or equal to, but you could put approximately 2 times the max of those, which would be 10 and 15. So that would be 30 kilohertz the way I see it. Sound good? Okay, moving along. The next question is, can the bandpass sampling theorem be used for this signal to get by with a lower sampling rate? So what I would do, especially if you're fuzzy on things, just draw a picture. So we've got something at 10, something at 15, we have something at DC, and then of course draw the negative frequencies if I want to. So I look at that and I say, if I didn't have the DC component, I might be able to think about that being a bandpass spectrum composed of 2 sinusoids, one at the lower edge of 10 and the other at the upper edge of 15. But that's not the question. The question is for the entire signal. So given that this signal has a DC component, according to our sampling theory, the bandpass sampling theory in the book, and that's the one I'm referring to here, not that homework problem setup, we can't do it because it says that it applies to a signal that is has zero spectral components below a lower band edge. So it assumes that you've got nothing down in here. The way I think of it, you probably could figure out something, but this is not strictly according to the theorem. That was not the intent of the problem. The intent of the problem was what was in the book and the theorem. What I think could happen, though, is if you were to undersample, let's just suppose I represent this as a blob like that. Just got a message from one of my capstone teams. Nobody knows I'm teaching now. Everybody thinks they're independently talking to me. No, that's okay. You're fine. This is class time. You're in priority right now. So what I was thinking of is I'm just seeing the messages flick onto my screen, and you see them too, right? Yeah, security breach. So there's DC, and if I had my two spectral blobs up here, just say that rectangle contains the 10 and the 15, we could undersample that, and the numbers we could work out. Those two spectral blobs could fill in, and then of course the images would go up. As long as we didn't touch DC, we could still recover what we wanted, right? We could get back the green, and as long as the spectral translates in blue don't cover the DC spectral line, we'll still have it. In general, that's what our theorem says, the one that's in the book. I'm going by the one in the book. But you can play games with it, and that's kind of what I did in that homework problem, which came out of another book on undersampling receivers and technique called IF sampling. But generally, when you do a bandpass sampling, you do something else, and that is you will put a bandpass filter around the signal from the get-go to make sure nothing else ingresses and starts creating mixing products, because that's what the theorem has to assume, that you've got a limited bandwidth that you want to undersample. In the case of having DC, though, you wouldn't really be damaging anything because it's not going to translate to anything but an image, a multiple of the sampling rate. Whenever we have sampling theory, we'd get this thing would repeat itself right over here. This would be like Fs minus Fs. The DC images again at Fs and 2Fs and so on. I don't want you to get too hung up on that, because at this point I was referring to the textbook, and strictly speaking, the answer is no. The last problem is just a multiplexing problem, kind of like the one I sketched out a couple of weeks back, and it's just a matter of putting together all the channels. I think because it is 4 o'clock and I want to spend enough time on the project, I'm not going to cover this one. I do have the solution ready to roll that I can push up there, though. It's just going to be kind of like an example I've worked already. You're going to have, 2 high-quality audio, each at 24 kilohertz bandwidth, 1 digital stream at 1 megabit per second, 2 more digital at 2, an analog voice channel having a bandwidth of 4, and 2 high-quality audio channels requiring 18 bits per sample. So this is just a conglomeration of things that I put together, and then I threw on this 10% related to this or the project. Or this, okay. Yes. No, multiplex means interleaving, or multiplexing as in a digital multiplexer. You're combining many things together. It's most closely related to the picture that I drew here, remember, for the hints page. We were talking about that earlier. It's this idea right here, where we're going to multiplex all the bits into a frame, and how they're organized in the frame is up to us. We could have interspersed with that parity check bits, synchronization bits, other things that might be needed, so that when it's received, you can unravel it and get all the bits put back and demultiplexed into the right output. Right? And I'm trying to think. Yeah, I'm just trying to think. It made my brain flash back to something that I got assigned when I was in industry to build some sort of a multiplexer for bits, and I can't remember. Yeah, well, no, we're not going to finish the quiz because I was going to move on to the project. I'm going to supply that to you later. I'm going to fill this in later. I've got a nice picture on my other computer sitting here, but I'm not going to go for it right now. I'd rather go on to the project because I know some of you are hoping you might have an excuse to get more time, but I don't really want to give you more time. I want you to just get it over with and get it done. So what I want to do is go talk about that. This is the project statement, but I guess what I wanted to do as the starting point was just go back to what I started to do last time, and then realized I had a mistake in my document, and I fixed that. And that is, let's see, pin folders. That's the wrong one. Yeah, that's what we're going to be talking about right now. Right. Yeah, here it is right here. Yeah. Yep, and that's the coherent. After that, well, yeah. Okay, so what you do after you build this thing up, and I don't remember the order because I'm just thinking off the top of my head, although I guess I do have my solution up on my other computer. Problem is, I can't use the same mouse, or I can't touch the screen. I've got two computers, one a touch screen and the other's not a touch screen, so my mind gets confused. I touch the one I can't touch, and I don't think I can touch the one I can touch. So I'm looking at task 2, I think it is. Let's see. Making sure I'm getting the right part. Maybe it's not task. No, it must be 3. You're talking about the part, though, where you're going to measure the signal to interference ratio, probably. Is that it? Or not? Because once you get the system put together, you're going to measure the signal to interference ratio for turning off one channel. Yeah, so it is task 2. So after it's all implemented, then you're going to I'm just seeing what I've got in my solution here. That's right. You don't have to call those in, you just supply that function, and then the top level function takes care of getting that in. So if I was to jump over to here, kill that, go into here, get down into here, the top level transmit function, it brings in all the Weaver modulators. So it's either going to drive the modulators with noise from these 3 wave generators, or it's going to drive them with just white noise from the random normal noise generator, a random number generator. So it's either this or this, and then that pushes into Weaver 3 times with the Weaver configured to set upper sideband, and then it drops in whatever carrier frequency you're calling for. It loads in your 8 kilosamples per second and just some other attributes that I have in here. Some of it's redundant the way I have it designed, but it is what it is. And then that gets transmitted. So that puts us back over to here. So we're sitting right here after we leave the transmitter. And then in the top level function, I also have a channel model which is composed of a bandpass filter, and that bandpass filter says you can only place your channels between 16 kilohertz and 32 kilohertz. So that filter is designed right here, not using my functions, but using the butter function, which is in scipy.signal, to just be a bandpass filter of 7th order, and then the signal that comes out of the modulators goes through that and comes out, and that's what finally comes out of this top level function. So actually the output of the top level function is sitting, oops, I always hate that when it does that to me, and I can't get it to shrink right now. It's being obstinate with my finger action. So the output of the channel is right there after the bandpass filter for the channel is applied. So the signal you get at that X, and this is at X, is had that bandpass filter applied, and that's what comes out of the transmitter channel function combination. And then you go on from there to build a bandpass filter to eliminate an image from getting in, effectively is what that's all about. So that's an image reject filter in a sense. And then you have a coherent demodulator. And then you downsample back to 8 kilohertz again, or 8 kilosamples per second, so you can listen to it in the audio player. And what you're going to do when you're going after performance modeling, though, is you put trying to think, did I have you test with noise or the speech? I can't remember. Okay, so it is with speech. So what you do is you first, what John, you did it, was it both or was it, I don't remember right now. I'm looking at my solution, but I can't see exactly. It's in task 2 is all I know. I'm just going to continue to outline it because I want to get this over with. Superposition of demodulated output signals. Measure the output signal to noise ratio. Band limited noise messages. Okay, so you use noise. So you're going to be using the noise input in this case. And what you do is you turn off, get this to work right. You turn off message 0 and message 2, and then you're going to be measuring power. So that means you're going to use variance. So you measure power of the desired signal. And that's with M1 turned on. And then what you do is you come along and say, okay, now I'm going to turn M0 and M2 back on, but I'm going to turn M1 off. So I'm going to measure power a second time. So I'm going to have power in signal, and then I'm going to have the ratio of that to power from adjacent channels. And that constitutes signal to interference ratio. So it's what bleeds into my allocated channel for the M1 message from M0 and M2 is what's in the denominator, and what's in the numerator is what comes in as that's desired. And then you repeat that exercise for M0 as being the desired, turn off M1 and M2, and then turn off M0 and turn on M1 and M2. And then you can measure, I think I say you don't have to do both, but do one or the other. Either the signal to interference ratio for the lowest channel or the highest channel. And intuitively, what does your mind tell you? Which should be the better of the signal to interference ratios? One of the outer channels or the inner channel? Okay, that's right. So, and actually there's a preponderance for it to go in one direction, but that I'll let you just kind of discover how that works out. So that's what you're doing there, and you're going to measure the power using variance, because that the variance of a signal is the AC power, and bar is something you've probably used if you're in Province Stats right now. Really? Are you're sure? No, that's okay. That's okay. It depends on the organization of the book. So, yeah. Yeah. Yes, it's double side, it's single sideband that we're receiving, but it's the coherent demodulator that's in the notes from chapter 3. Do you remember that? Or no? Okay. Okay. I can pop over there. I don't have that chapter loaded, but I can definitely get it up there if it doesn't crash on me. So this would be chapter 3. Right there. There's the coherent demodulator for single sideband. So this is page 331. And see what's going on here is the signal comes in. If I can draw on this. At FC, and either we have a sideband present like that, or we have a sideband present like that. And what's going to happen when I multiply by cosine of FC, I'm going to get the difference frequency, and it's going to pull down that image. It's going to pull down that signal to baseband, and then because I'm multiplying it by a cosine, what's going to come out over here is going to be totally correct. I'm going to end up, after I multiply it, it's going to be down at baseband, and it's going to be symmetrical again. Because we get an up conversion and a down conversion when we multiply by cosine. Remember, we have a positive exponential and a negative frequency exponential. And the same would hold true if it was the lower sideband, so it works in either case. But the issue with needing the bandpass filter is you're going to be receiving a upper single sideband signal, so what you've got in this project is you've got another channel sitting right there. And if you don't block that from getting in, then it will think that it's double sideband, and it will just bring that guy right in too, and you'll end up with this happening. Basically, they'll be overlapping like that. Is that believable? Okay, it's pretty cool. You ought to run the experiment without the bandpass filter in there, at least for yourself, to verify that you get another signal landing on top. It will be inverted spectrally, so it won't make any sense. It'll sound like a foreign language. It'll sound worse than a foreign language. It'll just sound like nonsense because it's spectrally inverted. So back over to this. So what I wanted to do is just I cleaned up the section on the spectra. And with the time that remains officially, I wanted to show you that I go through examples of all the filter types. This was the area that I had a mistake in. I designed the interpolator filter here, and if you don't design with an interpolation filter, you get all the spectral images from your signal that's 2 kilohertz bandwidth in the Weaver modulator. But with the interpolation filter, you get rid of all those images and you get just that orange spectrum. Then the next design is the bandpass that has to tune over some frequency range. It has to be programmable. But in this example, I have it going from 24 to 28, which is 4 kilohertz. And I just pick an example of that. What you will do in your project is you will make these 4 values be parameterized. So you'll have a shift factor put in there to move it relative to a frequency number that arrives from the outside of your or from in your receiver. You'll have an FC that drops in there, and that will design this bandpass filter for you. Yeah. It actually, if I go look in the block diagram, it kind of sits in between, but it sits right in front of it, so you can include it in there if you want to, right in the front. I'm trying to remember, I guess I need to go look at how I did it, whether I had it just in the top level or I have it in the D mod. Let's see. I have the bandpass filter in the D mod. That's what it looks like. And I call it a tunable bandpass filter. Yep. So it's in the function called SSB D mod is where I have it located. So it's your image rejection. In a sense, it's an image rejection filter. The image in this case is the upper sideband of the adjacent channel that you want to keep from getting in. Good. And then as I rolled down here, I went through that, and then I went through the downsampler filter, which has to be designed at 9600 kilohertz sampling rate, but it's going to be a low-pass filter at 4 kilohertz, and it ends up doubling as the low-pass filter that the coherent demodulator needs. it needs a filter at the bandwidth of the message after the multiplier in the coherent demodulator. So this will double as that, and then it will allow you to downsample from 96 back to 8 again. And I just showed some pictures of that. The final comment that I had in here was inside of these functions for the transmitter and the coherent demodulator, you've got to do math operations where you have to multiply by an array of cosine values or sine values times a signal. And what I recommend doing is when you come into those functions, you just create an index array from the length of a vector. And if it's a vector at 8 kilohertz, I would label it as N8, let's say, for an index array at the 8 kilohertz rate. And then if you're working later on with an upsampled signal, you would get the length of that upsampled signal and call that, make an index array from that, like this, call it N96, and just have these two index arrays available for creating sine or cosine arrays to multiply times an array. So you'd have something like, you might have x times cosine of something times N8, and then later on you might have something like x up times cosine of something times N96. And in Python, there should be a star, right? Asterisk for multiply. In Python, one-dimensional arrays are always going to be multiplied pointwise, unlike MATLAB where you had to do the point multiply. In Python, they have a special array type known as a 1D array, and that's the type that we use in signal processing most of the time. It's just a one-dimensional array. It's not a row, it's not a column, it's just called a 1D array. In those, you can add, subtract, multiply, and divide, and it always obeys the pointwise operation, which is natural, right? You'd like it to be that way, I think. It makes it easier to do your math. In my handwritten stuff, no. I'll just give you a quick example of that over here in this notebook. Well, I'm going to do it over in the Chapter 4 notebook since that one is already running. Stuff that I was going to talk about today, but I'm okay not talking about it at this point. So I'll add a cell in there. So what do I want to do? What do I want to make that? I don't have anything made yet, so just trying to come up with something that has a length. I'm going to say a vector of ones of length 100. I'll make it 10. And then I'm going to create N8, like I was calling it, will be a range of x, or a range of length of x. And then I can just take x times cosine of 2 times pi times n over 50, let's just say. Oops. I didn't make these things the same length. Length of x, that's 10. Oh, n was hanging out in here from something else. That had to be n8. Okay, so there's those numbers. X times cosine, that's this guy right here. And if I don't believe that, I could try to plot that because it should just plot. If I plot it as n, I do a stem plot, I guess. Stem of n8, comma, plug that in. And then to make things happy, I'll do this use line collection true so it plots nicely. And there it is. So it took on those values. So I didn't have to put a bracket or anything on because it just knows they're ND arrays. The point is they have to be the same length though. That's the important thing. So X has to be the same length as N8, but I've kind of ensured that, and that's kind of what I was trying to hint at over here, is you need to have some index arrays for doing some signal processing operations, and you're ensuring that they're going to match. And you don't have to worry about whether it's a row vector or a column vector, because in Python, ND arrays that are one-dimensional don't really have a dimension. And if you've not ever played with that at all, I can show you that too. Create a cell down here. If I take any ND array object and I type size next to it, it tells me what its size is. It's 10 elements. If I type shape, which is another attribute of an ND array, it will tell me that it is a tuple, but it says it's just 10 by nothing because it's a one-dimensional array. On the other hand, if I was to upcast this up into a 1 by 10 array, which I could do, let's just do that once. I could say y is equal to, and you don't need to do this at all, so this is just kind of something to go explore. If I put square brackets around this 1D array, now it's going to become y dot shape is going to become a row vector. So it's got 1 row and 10 columns. Does that make sense? And if I was to put a dot T out here, what do you think that's going to do? Think matrices. T would be what in matrix theory? Transpose, right? There, it's transposed it. So if I went and displayed it right here, I'd have a matrix, and it uses brackets, Python does, for the row. So there it's a column vector, and here it's a row vector. And see, there's an extra bracket out here indicating that this is a two-dimensional array because it has a pair of brackets, but it's composed of 1 row. And if I need to take that away, I can do my brain's going to draw a blank, so I hit tab here. It was in my brain and then it just flicked out of it. It's not shrink, it's called, it's not collapse either. There's a name for it though, I just can't think of it right now. I'm not getting my help on that either. It'll take it down to a 1D array again if you want to do that, but we didn't need anything more than 1D arrays in this work, so oops, let me get rid of that. If you have some other questions, we're over time, but some of you might have a class to go sit in on next, and I don't want to interfere with that. Okay. Well, I'm going to sign off then and start processing my video, and I've got a video conference to do for my real-time DSP class. The student has to demo some work to me from his midterm, so I'm booked in myself. Yeah, that's fine. Slack is working okay. It keeps me maybe too busy, but I'm liking the idea of using it now because it puts everything in one location for me for everything I'm doing with all the students I'm interacting with. So I'm not sure I'd want to use Canvas or not because you must like it a lot. Yeah. Yeah. Well, I kind of like this industrial tool. This is a work kind of a tool as opposed to just for teaching. So you may end up working for a company that uses messaging software like this. Probably Microsoft Teams, though. Microsoft's trying to take over the market in this area. Slack was one of the first providers of a service like this, but now Microsoft is trying to steal the show from everybody, I think. That's the impression I get, at least. But yeah, maybe someday, but I think that someday is going to be not applicable unless they force my hand before I retire. I don't know. So I'm going to stop sharing, and I'm going to get the video under production and start my next video conference up here. So, yeah, same to you. Same to you. And anybody can Slack me with messages if they want to talk some more later. I've got 2 conversations on deck right now, though, or maybe more based on what I received while we were talking. Okay, bye for now.